Hey guys, so for my final project, the material I chose to select was stainless steel. This material really interested me because it was something my dad and I use a lot at home. We use some of our homemade engineering skills to build things for our boat and other stuff that deals with the elements outside. To enhance my report, I really wanted to give you a presentation on the mechanical properties and a little bit of the chemical properties of stainless steel 304. Part of the reason I chose stainless steel is because I know how special it is under certain weathering conditions. So yeah, let's get started. So first, I'm just going to give a little bit of overview of what we're going to talk about. So first, we're going to go over the common ways that it's used, and then we're going to talk about the stress strain diagram and how to read some of the data on that. And then we're going to talk about the hardness and why that's important, and then the chemical structure and the crystal structure. So common uses, cookware, it's very ductile and it transmits heat very well. So it's perfect for pots and pans and things like that. And they're also around water, and stainless steel is very resistant to rust. So with all those combined, it's really good for cookware. It's also used in the food industry for machinery. It lasts a while, and we can really see when the parts are starting to go bad because it's a ductile material and there will be plastic deformation present. Fasteners like nuts, bolts, and washers. Now, here they're used kind of sparingly. They're used in environments that are really wet or high wind or things like that where they're really getting into the elements of being outside. Marine equipment, so like boats and steel plates used underwater, very resistant to rust. And chemical containers. So I think this looks like either a wine place or a beer place or something, but the insides of those are moist all the time because of the fluid inside of them. So they have to be able to resist that. So the stress for strain diagram, they're very important for engineers. We can obtain information from the graphs that let us calculate for deformation, change in length, and change in area when a force is applied. Every test is slightly different because, not every piece of steel is exactly the same. This is just one example of a stress for strain diagram from one experiment done for stainless steel 304. It is important to see uh, the re the reactions of steel for one specific test, but we like to look at an average as engineers. So being able to see how multiple pieces of the steel react is what we look for. So here's a little bit on the data that we can pull. So Young's modulus is the modulus of elasticity, or basically you can think of it as how resistant to deformation it is and the rate that deformation occurs. So this only occurs in the linear region, which is right here. Hopefully you can see on my mouse. So you can see that it's a straight line all the way up, and then you get to a point where it starts to curve off. So this is important because this applies to all of our equations for solving for stress, strain, things like that, the change in the area, change in length, stuff like that. Yield strength. Yield strength is definitely not yield stress here. There's a big difference. So yield strength would be kind of right where that plastic deformation starts to occur. It's the point where it no longer is elastic deformation, which means it'll come back to its original length. This is where plastic deformation starts. So for this material, it looks a lot higher than where the linear region ends. So here it looks about maybe 500, where it starts to kind of curve off, maybe a little bit higher even. So like I said, every material reacts differently. And then tensile stress, that is the maximum stress that a material can undertake while being under some sort of stress. So here, the yield stress is more like the tensile stress here. So it's 1400 megapascals for this specific one. But the difference between 505 and 1400 is, if you look, this stainless steel goes through a strain hardening phase. So that means as it plastically deforms, it actually gets stronger. So it can withstand more stress over time. So hardness. What is hardness? Hardness is when, say, you have a scratch on a material or an indentation. It's how resistant to that is your material. So there's a lot of different ways that we test for this. We have a bunch of different scales, and they're all based on different measurements, but they all kind of have the same principle. They use this diamond press, and they press in the material with a certain stress or force, and we can see how big of an indentation they make. So it's more like a ratio of, I want to say, the radius of the indentation, and they just take certain measurements. So we have Vickers scale, Brunel scale, the Knoop scale, and the Rockwell scale. So below in the YouTube video links here, I have the first video, which just gives an overview on the two main types of hardness scales that are used for stainless steel. And I think they were Brunel and Vickers. And then this YouTube video is a full demonstration of the Brunel hardness test. It's not on stainless steel, but it's still on, I believe, a piece of steel. So chemical structure. Um, Stainless steel 304 has an FCC crystal structure. So there's two types of phases. There's the austenite phase and there's a ferrite stage. Stainless steel 304 is in the austenite stage because it has a certain percentage of chromium and nickel in it. So the differences we can see here is it changes from a BCC stage to an FCC. So we have our iron atoms in the faces, and then interstitially, that's where all of the other impurity atoms fit into the crystal structure. So we have carbon here, and there might be a nickel here or a chromium. It's not exactly the same for each piece, so it's hard to get a definite crystal structure. So like I said, the interstitial space is filled by the impurity atoms. And then one interesting thing is when you look at a material, especially in this picture here, you can see that the chromium is more towards the top or the surface of the material. This is because the chromium forms the outer layer on stainless steel that makes it corrosion resistant. It has a chemical reaction with the oxygen in the air, and it creates an oxide layer between the material and any other thing that comes in contact with it. So that's why stainless steel doesn't rust and it's more corrosive resistant. So yeah, that was all I had. This is my works cited. If you guys have any questions, let me know. And yeah, I hope you enjoyed the video.